All right, so moving on to flight controls here. That's Chapter 6 in the Pilot's Handbook of Aeronautical Knowledge. We've talked about the axes of control, how we have
longitudinal, lateral, and vertical.
right, and how we have roll, pitch, and yaw. So our control surfaces on the wings, on the trailing edge, we have ailerons, which move up and down opposite each other and roll the airplane left and right, right? So the ailerons create more lift on one side and less lift on the other, right? To roll us left or right. So the way that they do that, and this is something that you don't necessarily think about, is what they're essentially doing is they're changing the angle of attack of the wing.
Mm-hmm.
So if the angle of attack of the wing is, say maybe 5 degrees, well, now we deflect the aileron downwards. Well, now if you draw a line from the leading edge to the trailing edge, even though the wing itself may be at 5 degrees,
Mm-hmm.
The average may be 6 or 7 now, because the aileron is deflected downwards at a higher angle, so the average of the wing and the aileron
Mm-hmm.
average together is more.
Right.
And that creates more angle of attack, more lift on that wing, and that wing goes up. If you deflect the aileron up, well, now the average is less than the angle of attack of the wing as a whole. Less angle of attack creates less lift, and the wing goes down. When you do that, though, if you think about it, we talked about how creating lift creates induced drag, right?
Mm-hmm.
So when the aileron moves down, that creates more lift to push the wing up. It also creates more induced drag, so it pulls the wing back, right?
Which
so
makes a plane fly this way to return.
Right. So when the wing lifts up to turn the airplane this way, it also pulls that wing back, so which pulls the nose towards the outside of the turn, right?
Right.
So when we roll into a turn, we have to add rudder into the turn to counteract the fact that the aileron, which is pushing the wing up, is also pulling us
Right.
towards the outside of the turn.
Coordinated turns.
That's called a coordinated turn. And the rudder on the vertical stabilizer back here moves left and right, and what we primarily use it for is just that, counteracting the outside pull of the ailerons in order to keep us flying nice and straight as we enter a turn. Obviously, we also use it to steer on the ground, and we use it to align the airplane with the runway when we're doing a crosswind landing. We'll get into that later.
Yeah.
And then we have the elevator on the horizontal stabilizer here, which deflects down or up to pitch the airplane up or down. And those are what we call our primary flight controls.
Yep.
Elevator and aileron, which are in the chief is the yoke,
Mm-hmm.
and rudder, which is on the pedals.
Correct.
There are various different ways that ailerons can be built in order to minimize that tendency to pull towards the outside of the turn, which is called adverse yaw. When the aileron pulls the nose towards the outside of the turn, you have to use rudder to keep it going straight. There are various designs of ailerons that have been come up with in order to reduce that and make it so you don't have to use as much rudder in turns. And they go into detail on that, pages 6-4 and 6-5 here of the Pilot's Handbook of Aeronautical Knowledge. Talk about the elevator here on 6-6, 6-7. Some airplanes, instead of having an elevator, which is just the rear portion of the horizontal stabilizer moving, the whole stabilizer itself moves, and that would be called a stabilator. That would be like what the Cherokee that the Corbin Foundation has at Wanakee has a stabilator, which can be more efficient, but is also
Much more sensitive, isn't it?
it's more sensitive, and it also creates, because the whole tail has to move, you need a lot more structure back there,
Very stressful.
right, to make it strong enough to make that work. So it can be heavier. But it's more aerodynamically efficient. So because the whole tail is moving, so rather than only half the tail moving, which creates some amount of turbulent airflow, if the whole tail moves, that keeps the airflow nice and smooth. It's more efficient, helps it to go faster, but it's heavier. So that's something that designers have to balance is do they want to use an elevator, which is lighter and simpler, but creates a little bit more drag, or do they want to use a stabilator, which is heavier, but creates less drag? Then you get into flaps, which are usually inboard of the ailerons on towards the fuselage, and those come down together. And we talked about how when the aileron goes down, that increases the average angle of attack of that wing. Well, the same thing happens with flaps. As flaps go down, it increases the average angle of attack of the wing.
Mm-hmm.
And but also because the forward portion of the wing is at a lower angle of attack and the back part of the wing is at a higher angle of attack, it delays the stall because the stall happens relative to the angle of attack of the forward part of the wing, or the main part of the wing, but the flap at the trailing edge creates more lift. It essentially allows you the wing to fly at a higher angle of attack without stalling, which allows you to fly slower, which can be advantageous for takeoff and landing, but it's heavier, it's more complicated, and on light airplanes like the Chief, the designers decided it wasn't necessary.
Plus, when you're going slower, your control surfaces need more deflection to be effective too, correct?
Right, correct. And then you can also have devices on the leading edge of the wing, flaps or slots that open up to increase airflow over the leading edge of the wing to delay the stall as well. Jet airliners almost always have those.
They go way down.
They go off the leading edge of the wing down to create what that essentially does is it reduces the angle of attack at the leading edge of the wing even more, in combination with the flap at the trailing edge, increasing the angle of attack at the back.
Scoop on there.
Yep, basically turns into a big scoop, so that as the angle of attack increases, it just doesn't want to stall and doesn't want to stall.
Creates a bigger under camber on your wing to make it float better.
Yep, and you get more lift at a slower speed. Good picture of that kind of a thing on figure 6-19 here, although that's actually
those are spoilers.
Spoilers as well, which come up just ahead of the flap to allow air to basically come through the wing and therefore make it so it doesn't create lift, and that drives the airplane down onto the runway so you can...
Some ultralights have spoilerons.
Right, so those would activate...
They're like ailerons. I used to build ultralights when I first got married. We didn't have ailerons. We had two spoilers. When you do the stick left and right, one would pop up like an aileron to kill the lift on a wing, and then if you turn the stick, they both popped up to kill the land. So that's... Yeah, they used them like ailerons, but they weren't really ailerons.
Yep. And one final thing, trim tabs. So on an elevator, when an elevator deflects downwards, obviously the air wants to push it back to center. Or if it deflects upwards, the air wants to push it back to center. So what you can have is a trim tab, and this shows it in figure 6-20, where the trailing edge of the elevator deflects downwards, and that pushes the elevator up, which causes the airplane to pitch up. Or if the trim tab deflects upward, that creates downforce, pushes the trailing edge of the elevator down, and that pitches the nose down. And by doing that, what you're essentially doing is you're adjusting the speed at which the airplane is in equilibrium. So if you trim nose down, the airplane will speed up until the nose wants to come back up again, and then it'll be in equilibrium. If you trim nose up, the airplane will pitch up and slow down until the nose wants to come back down again. It'll be in equilibrium. So when we talk about trimming nose up, what we're really talking about is trimming for a slower airspeed. And when we talk about trimming nose down, we're trimming for a faster airspeed. So that's why after we take off and we level off at cruise and accelerate to our cruising speed, we trim nose down to set the airplane's equilibrium for a faster speed. Or when we go to land, we want to slow down for landing, so we trim the airplane nose up to put the airplane in equilibrium at a slower speed, ready for landing. And that's a trim tab. You can also have Other methods of trimming, like on Piper Cubs, where they actually move the whole horizontal stabilizer for trim, nose up or nose down.
I didn't know they did that.
Yep. If you ever look at Piper Cub, like a couple of the people in the EAA chapter locally
I'll have
here
to
in
check them
Madison
out next time I see them.
have a Piper Cub, you'll notice there's kind of a slot at the leading edge. If you look inside there, there's sort of a screw that pushes the front of the horizontal stabilizer up or down, and that's how they do the trim.
I've seen that, I just didn't know what it was.
Yep, that's what it is. And that pretty much, and you can see that in figure 6-23 here, it shows how that works.
Yeah.
So that pretty much completes our first ground school lesson. We've talked about aeronautical decision making. We've talked about the physics of flight. And we've talked about the flight controls. Next time we'll get into aircraft systems. And of course we'll review anything that, Philip, that you have questions about for next time.
Sweet. Well, thank you, sir.